Evet, herkese merhabalar. Yavaş yavaş katılımcılar da gelmeye başlıyor gibi gözüküyor. Ufaktan başlayabiliriz sizler de hazırsanız. Öncelikle Interface firmasıyla beraber düzenlemiş olduğumuz webinar serimizin ikincisi olan Tork Sensörlerinin Çalışma Prensibi ve Seçim Kriterleri adlı webinarımıza hepiniz hoş geldiniz. Kısaca kendimden bahsedeyim. Ben Ulaş Taç. Katılımcılara baktığım zaman çoğunuzla geçtiğimiz dönemde belli görüşmelerimiz olmuştur. BİAS mühendislik firmasında satış ve uygulama mühendisi olarak çalışmaktayım. Interface firmasının ürünlerinin satış ve satış sonrası süreçlerinde destek olmaktayım. Bu alanda çalışmaktayım. Webinar serilerimize olan yoğun ilginiz ve katılımlarınız için teşekkür ederiz. Sizlerden gelen talepler ve sorularınız paralelinde belirli aralıklarla faydalı olabileceğini düşündüğümüz konularda webinarlar düzenlemeye devam edeceğiz. Bu kapsamda eğitimlerimizden, webinarlarımızdan, arada düzenlemiş olduğumuz sempozyumlarımızdan, etkinliklerimizden haberdar olmak için bizim LinkedIn sayfamızı takip edebilirsiniz. Güncel olarak orada paylaşımlar yapıyoruz. Interface firması ile beraber gerçekleştirmiş olduğumuz webinar serimizin ilkinde load cell teorisi ve seçim parametreleri üzerinde görüşmüştük. Bu alanda bahsetmiştik. Webinarımızın sonunda bu ilk webinarımızın da olmuş olduğu kaydı sizlerle paylaşacağım link olarak. Şu konuda da sizleri bilgilendireyim. Webinarımızın sonunda bir soru cevap kısmımız olacak. Sorularınızı sohbet kısmında yazılı olarak bizlere iletebilirsiniz. Webinarımızın sonunda bunları teker teker cevaplandıracağız webinarımızın sonunda. Ben çok fazla zamanınızı almadan sözü konuşmacılarımıza devretmek istiyorum. We will have two presenters today from Interface Company. First presenter is Mr. Jeff White, who is Sales Director. And our other presenter is Skidmore, who is Custom Solutions Sales Director. On behalf of BİAS, I would like to thank you, both of you, for your great support, interest, and waking up so early for us today. Now, I would like to invite Jeff and Keith for start the presentation, please. You can take the management and share your display.
Sure. I'll start. Hello. Good afternoon, everyone. Good morning from the United States. My name is Jeff White. You might remember me from Load Sales 101 back in February. I'm the International Sales Director. I work closely with ULAS and the BIAS team on load cells and torque-related applications. I am truly lucky to have Keith aside me today, as he is the expert on many of our more in-depth product lines, including torque sensors. So I'll let him take you through this presentation and hopefully spark some ideas for applications you might have in the future. Keith, I'll let you introduce yourself while I get this going.
Hi, everybody. My name is Keith Skidmore. I've been with Interface for about 25 years, been product manager and sales for Interface that period of time, and have focused, as Jeff says, on some of our specialty products, which includes everything but your basic blue load cells. So here we are.
Yeah.
Right. I'll take you through the presentation, and Keith, away we go.
Well, today we will be talking about torque transducers, design and working principles, basically how they work and what the technology is behind them. There are different types of torque sensors, ones that rotate and ones that do not. We call the ones that do not rotate static or reaction torque sensors. There are also different sort of styles or types of torque sensors, flange style, shaft style, specialty types. Couplings are the devices that are used to attach torque sensors to the other components in the test string. For mounting torque sensors, they can either float or be fixed mounted. We're going to talk about the difference and pros and cons of each approach. Talk a little bit about bearings and accuracy and resolution of the torque sensors, how to choose the right capacity capacity selection can be a little trickier with torque than with other sensors. Again, talk about RPM considerations a little bit, some common features of or specialty features of torque sensors, and then review a few applications. So what is a torque sensor? A torque sensor converts a mechanical input of torque to an electrical output signal. The signal is directly proportional to the torque input. Basically, it's a metal spring element or flexure, just like a load cell, except it's sensitive to torque instead of force. We have foil strain gauges that are bonded to the metal flexure spring element in a Wheatstone bridge configuration. And then torque applied to the sensors causes either bending or shear strain in the gauged section, and that causes strain gauges to change resistance, which generates an output voltage signal proportional to torque. So the output inherent in any of the torque sensors that we are going to talk about today are millivolt per volt outputs, and then any different kind of signal that may come out of the torque sensor would be due to some type of processing. But inherently, the basic measurement device is a strain gauge based sensor. Next slide. So basically, you can have a square shaft or a solid round shaft. Some torque sensors get a little more complicated in that they have features on the shaft, such as machining it down into a cruciform, such as shown on the left, or even more complex shapes, I-beam type shapes, T cross sections. But basically, they all do the same thing. As you apply a torsion, the strain gauges or the strained area is where the measurement is made. These different shapes of torque sensors can help, say, isolate the strain to the strain gauge area and make them less sensitive to, say, extraneous loading, such as the one on the left versus the one on the right. Also, lower capacities lend themselves to more machining of the strained area, such as shown on the left. So reaction or static, and we'll use that term interchangeably, measures torque without rotating. And so basically, if you have a regular Wheatstone bridge type sensor, there will be a cable that's attached to the sensor for the power to the bridge and the signal coming from the bridge. And so with a static sensor, that cable is attached directly to the sensor. And if you were to spin the sensor, the cable would spin along with it. So the sensor can rotate through some minimal amount of rotation, but if it were to spin round and round, the cable would get wrapped up. So a reaction sensor has a cable attached to it, which prevents it from spinning round and round. A rotary sensor, on the other hand, uses some type of scheme to allow it to spin round and round and round without the cable becoming an issue. And that could either be slip rings, could be rotary transformers, could be a rotating electronic scheme with, say, induction power transfer, could be digital or analog. Can even use radio telemetry to broadcast the data signal across using, say, 2.4 gigahertz Wi-Fi, for example. And basically, a reaction sensor is at the heart of every rotary sensor. So basically, you make a torque sensor, and then instead of soldering a cable to it, you add extra things to the sensor to allow it to rotate. Next slide. So this is just an example of a digital rotary torque sensor. You can see there's a shaft. Hopefully you guys can see my cursor. Maybe not. Anyway, there's a shaft, there's a drive side and a measuring side. The difference is there's more inertia, moment of inertia on the drive side, more mass because the electronics are mounted to the drive side. See, there are some bearings. There's an induction coil called a rotating transformer, and that is for power and signal transfer. And then there's a microprocessor on the shaft, a strain gauge amplifier, an analog to digital converter, and then the digital signal is basically pulsed across a transformer back to the stator side, and then it's further processed with a digital to analog converter to create a plus or minus 5 volt signal. Because there's a microprocessor on the shaft, we can also send a command to the shaft to close a shunt. So some rotary torque sensors actually do have the ability to have a shunt on the shaft. It's not possible to connect a shunt resistor across an induction gap, but again, if we can send a command to the shaft to close a switch, then a shunt can be enabled on the shaft. The advantage of a shunt on the shaft is that it shunts the strain gauge bridge, creates a signal from the bridge, and then that signal is processed and transferred to the stator and then amplified into your signal conditioning or external signal conditioning. And basically everything downstream of the bridge can be checked, double checked, or used for scaling. Next slide, please. So this is an example using a reaction torque sensor with a rotating shaft on a motor. And so they may say, hey, well, how does that work? If we have a rotating sensor, that makes sense, but how can we use a reaction sensor to measure rotary torque? And here's a very simple scheme where you have a hollow torque sensor. So the blue sensor in the middle is hollow. There's a hole going all the way through the middle. We have a motor mounted to one side of the torque transducer, and you have the other side of the torque transducer mounted to a plate, and then there's a hole in the plate. So the motor shaft spins through the torque sensor. The housing of the motor is attached to the torque sensor, and as the shaft is loaded, the housing of the motor tends to want to spin in the opposite direction of the shaft, and it's held from spinning using the torque sensor, and it's a reaction torque. So that's why we call these reaction torque sensors, as well as static torque sensors. So the reaction of the motor housing is equal and opposite to the torque in the motor shaft. Very common approach. This is much simpler than using a rotary torque sensor and can be a preferred approach depending on the application. Next slide, please. So these are some other examples of using static or reaction torque sensors to measure rotating torque. On the left side, we have motor torque, and the right side, we have brake torque. And you can see they both have the same components. You have a motor and a brake and a torque sensor, but the difference is what is intended to be measured. Motor torque side, we're actually trying to measure how much torque the motor produces or how much power the motor produces. And so we can mount the housing of the motor to the torque sensor. So the torque sensor is rigidly mounted to the plate on the left side. The housing of the motor is rigidly mounted to the top of the torque sensor on the right side. And then the brake is mounted to the plate on the right side. So the motor shaft is spinning the brake engages, and you can use a brake to load the motor and measure how much motor torque there is. On the right side, we are measuring brake torque, and basically the same setup, except now you've got the motor attached to the plate, you've got the motor shaft spinning the brake, and then you've got the brake housing attached to the torque sensor rigidly mounted to a plate. Say, what's the difference? Well, under static, steady state conditions, there is no difference, but you've got more mass coupled in one direction or the other. And I don't know if that makes sense, but what I'm trying to say is that if you're trying to measure brake torque, you want less mass attached to the brake. So if you're trying to see dynamic torque conditions, less mass, less mechanical filtering is better. And so basically the torque sensor should try and be attached to the live end of the torque sensor should be attached to the thing that's trying to be measured. So that's the difference between these two setups. Next slide, please. Oh, by the way, back up a slide. This conceptually is a great idea. In practice, it may be difficult to mount a brake or a torque sensor to a motor or a brake to a torque sensor because of practical considerations. The motor housing may not have appropriate mounting holes. It might be a base mount that sits on a plate, for example. So this conceptually makes a lot of sense. In practice, a lot of times these approaches don't work as well because of the fixturing requirements, and a rotary sensor would then be used instead. But conceptually, this works great. Next slide. So here we have some examples of rotary torque sensors. That specimen on the right could be a brake, could be another motor. And then on the left, we have a loading machine, which would be an electric motor in this case. You have a flange style torque sensor sitting in the middle. we have flange adapters attached to each side of the torque sensor. We have couplings attached on the right side, and that's a double flex arrangement on the right side. And then, of course, your specimen. And then on the other picture, we have a motor and a fuel pump. And we have a pedestal mount torque sensor in the middle and double flex couplings on each side of the torque sensor. You may wonder what the difference is between these two pictures. The couplings on the right side are both double flex, and this pedestal mount sensor needs freedom of movement of its shaft on each side of the torque sensor. When I say movement, I mean for radial and angular displacement. And on the left side here, picture, we have a double flex coupling and a floating sensor. So the T27 is actually a bearingless sensor. It's being supported entirely by the motor shaft, and then the double flex couplings on the right just allow for misalignment between the specimen and the motor shaft. Next slide, please. So some photographs of actual dynamometers that are using load cells as reaction mounts for the rotating or the tendency of the dynamometer to rotate. So on the left, that's a big eddy current dynamometer that is gimbaled on bearings. And again, as the shaft is spun, say by a internal combustion engine, the housing of the eddy current dynamometer wants to spin along with the shaft, and the lever arm held by a load cell creates the reaction that prevents it from spinning, and that can be used to calculate torque. Distance of the lever arm times the force measured is torque. And on the right side, a little bit different looking system, but quite similar, where there's a lever arm and an S-type load cell providing the reaction. So instead of a reaction torque sensor, you can actually react torque using load cells. And that's what this is an example of. Sometimes this could be easier, less expensive, less complicated, depending on the system. Again, mechanically, a lot of systems don't allow themselves to be mounted such that a reaction load cell can be used. Again, if it were, say, an electric motor mounted on a base plate, much more difficult to do this than a dynamometers that's been designed to be mounted on bearings on each of its ends. Next slide, please. So shaft style versus flange style sensors. Shaft style sensors basically have a shaft that goes all the way through the sensor. It's one piece. That shaft has a section in the middle that has strain gauges adhered to it, and it might just be a straight through shaft, or it might have features machined into the shaft. A lot of times the shaft measuring element is much, much smaller than the shaft end. So sometimes customers see, a big, 32 millimeter shaft and think it's beefy and strong like a 32 millimeter shaft might be. But in reality, the center section may be quite a bit narrower. So that's just something to remember. And the shafts can either be smooth or keyed, and keyed shafts can either have single or double keyed versions. And then in Europe, typically the keyways are well defined per a DIN 6885 spec. But keys are okay, but we do prefer smooth shafts, and most of the torque sensors that we sell with shafts are smooth shafts. So a smooth shaft, you have a more uniform introduction of the torque into the measuring shaft, because the couplings actually grip the shaft all the way around this perimeter instead of engaging a key. And then also those type of gripping couplings can come apart easily. You can, unscrew or loosen the bolts and it'll come back apart. They also have zero backlash, and backlash is important, and it's bad if you say reciprocating, changing torque direction, or even changing torque levels. Backlash allows the shaft to slip a little bit inside the coupling, and that's undesirable. A keyed shaft is simpler and may cost less, but the key can wear. You can have backlash, especially in reciprocating applications, or for keyed connections. A lot of times an interference fit is recommended. The problem is if you use an interference fit with a keyed hub on a keyed transducer shaft, it becomes very difficult to remove the hub the coupling hub without damaging the transducer shaft. In fact, the transducer shaft may very well be damaged installing the hub, and then when you pull it off, it damages it further. And so torque sensors are expensive. They're not intended to be consumed, and so it's best not to use couplings that damage the shafts. Also, if you can't get the couplings back off, it's very difficult to have the torque sensor calibrated. So we have had situations where a customer sends us in torque sensors to calibrate. They have giant couplings attached to them that have been, say, heated and press fit onto the shaft ends, and we can't get them off. And so basically the whole entire assembly becomes uncalibratable without manufacturing very expensive coupling pieces to fit into the calibration machine to calibrate it with the couplings attached. Flange style sensors, typically a lot shorter than a shaft style, and they have pilots for centering. So whenever you're attaching rotating elements together, there should be features that allow them to be concentrically located one to the other. So flanges will have pilots for that. Like I said, they're quite a bit shorter. In test benches, a lot of times test bench real estate is at a premium, so a shorter drive line can be desirable. Next slide, please. These are some examples of shaft-style torque sensors. You can see on the left is a floating design intended to be attached by its shaft ends to the drive line and not mounted on a plate or anything underneath it. In the middle, we have a pedestal mount sensor, which is designed for the housing to be mounted on a plate. And then on the right is actually a reaction type sensor, shaft style. It may look like a rotating sensor, but in fact, that housing is attached on one end to the shaft. So it's just a rotary shaft sensor with a housing attached to it without any bearings or anything. So this one cannot spin, whereas the one on the left has bearings and can spin within its shaft. So shaft style, she said, convenient mounting with standard shaft style couplings. Shaft style couplings are readily available. And again, there are plenty to choose from that have a gripping feature so that they grip onto the smooth shaft and then can be released later. These are typically longer, as we said, than flange style sensors. Typically have bearings, and again, can either be smooth or keyed shafts. The examples here all show smooth shafts. Here we are showing some flange style sensors. See, some of them have through holes through the middle, which helps accommodate the reaction torque mounting where the motor shaft may pass through the sensor. Some of these are bearingless rotating sensors. So the ATQ, which is in the lower middle, and then the upper right, we have a T27, which is also a bearingless sensor. Then the rest are reaction type sensors are not intended to rotate. Again, these can rotate, just it's limited by the cable. And so if you say had a valve test that's reciprocating back and forth over 90 degrees, reaction sensor may be preferred. You just have to manage the cable so it doesn't get worn out from moving back and forth. So flange style, as we said, short installed length, better resistance to overhung moments. Plus, because it's shorter, the actual overhung moment due to mass hanging on the drive line can be significantly less. Can be more convenient to mount, although it's not as easy to find couplings for shaft style sensors. So a lot of times, it's not as easy to find couplings as it is for shaft style sensors. So may have to make adapters and things. Can be hollow, which can be useful. Bearingless rotary torque sensors tend to be flange style. See down in the middle bottom is a special reaction torque sensor, which is called a C-face, and it mounts to a standard NEMA C-face motor. So again, when we say we're going to use a reaction torque sensor to measure a rotating torque, one of the obstacles to doing that sometimes can be fixturing a motor may not want to mount to the torque sensor. Well, turns out there are specific motor types that are called NEMA C-face motors. And if that type of motor is selected, then a C-face torque transducer can be used to mount between that motor face and a plate or something. And typically the motor mount would be on the front. So the front of the motor mounts to the torque sensor of the shaft, goes through the middle, and then the other side of the torque sensor can be mounted, say, to a base plate. You notice too that C-face sensor has a very large hole, and that can be good because another issue you have is if you mount a motor to a hollow torque sensor, a lot of times the motor shaft isn't long enough to stick through the other end of the torque sensor, so you have to adapt the shaft. Well, how do you do that? Maybe with a coupling. Well, that's challenging if the hole in the torque sensor is only about the same size as the shaft. So the C-face has a very large hole to accommodate a coupling on the shaft end that can then adapt to another shaft. Yeah, thinking back, another reason for hollow torque sensors is sometimes customers want to run lines through the rotating assembly, such as hydraulics or pneumatic lines or electrical thermocouples and things. Here we're showing some specialty torque. There are a number of products in the market that are very specific to certain applications. On the upper left, there is a pulley torque transducer that actually mounts on a motor shaft, and the pulley mounts to the torque sensor. Typically, if you were to try to mount, say, a pulley on a torque sensor, the pulley tension or the belt tension would ruin the torque sensor. So a pulley torque sensor is a special device that allows the pulley to be mounted to it and can take the very high tension loads of the belt without damage. On the right is an actual coupling torque sensor where the coupling is integrated into the torque measurement. So part of the coupling is actually manufactured as the torque sensor and the strain gauges are applied. And this would be a bearingless type torque sensor with the induction ring around the rotating assembly. And then on the bottom is a very, very small capacity torque sensor. It has a flange mount with a spigot or a pilot on the left there, and then a tiny little shaft sticking out on the other end for measuring very small torques. That might be used for something like a catheter test or, very, very small bearing test, for example. So couplings should be used for all torque installations. Some people say, oh, why do I need to use couplings with a reaction test sensor? Well, we use them in our calibration rig, for example, when calibrating reaction torque sensors. They should be used. They sometimes aren't. The customer does that at their own jeopardy. What a coupling does is ensures isolation of the torque loads. A coupling will transfer torque loading to the sensor, but will not transfer extraneous loads. So just like a load cell, they're sensitive. Torque sensors are sensitive to off-axis loading. Those loads create errors. They also can damage the sensor. So coupling prevents that. Without a coupling, a misalignment in the driveline can create large bending loads and side loads into the sensing elements that are, at the very least, damaging, or I should say, at the very least, error producing, but it also can ruin the sensor, which is not desirable at all. So couplings, again, extraneous loads can cause measurement errors, and they can be as much as 1% of the applied bending moment. And it's really hard to say how much bending moment there is. But if you say you have two shafts, they're not perfectly aligned, and they're never, ever perfectly aligned. So say the shafts are non-concentric by, 1/10 of a millimeter, which seems like a small amount. What happens if you try and bend those shafts so that they are now exactly end to end? One of the shafts has to bend 1/10 of a millimeter. Well, what does that do? That could take 1,000 pounds of force to make that happen, right? So that's what happens when you say bolt two shaft ends into a solid coupling. You're forcing them into alignment, which creates large bending loads. On the other hand, a coupling does the same thing, but with a very soft element in the middle, such that the shafts are not bent into alignment. The errors due to, say, bending loads are superimposed over the measured signal. So you have a torque and a signal due to that torque, but you also have an error signal that is superimposed on the torque signal. And then the frequency of the error signal will be proportional to, whoops, I typed some wrong things in there accidentally. Anyway, the frequency of the error signal would be proportional to RPM. So basically you might have one cycle of the error signal per every rotation of the shaft. And as it rotates, 1,000 times a minute, you'll have 1,000 per minute error component that you can filter out. But if you're trying to look at dynamic torque, you may not want to apply such a heavy filter. Again, wear on the sensor is another issue. Bending of the shaft, if you have bending and then it rotates, it's just like bending it back and forth a bunch of times, can definitely prematurely wear out the sensor. Also bearing loads. A bearing style sensor has bearings that are not at all intended to do anything but allow the shaft to rotate inside the housing. And so if you have side loads or bending moments that create bearing loads, those are going to wear the bearings out. That's the last thing we want, because it's not a rebuildable bearing that you just, buy a new bearing and replace. It means the entire torque sensor has to be rebuilt, recalibrated, remanufactured. So use couplings. Moving on. So we have different types of couplings. A single flex or a half coupling is a single flex point, and it only allows angular displacement. And then a double flex or a full coupling has two flex points and allows both angular and radial misalignment. And as you see in the bottom left here, that's a single flex coupling on the left, and it only has an angular displacement capability. Now, if you take two single flex couplings, which we also call a half coupling, and you say mount them together, it becomes a full coupling or a double flex coupling. And that allows for both angular and radial misalignment, as you can see by moving the two angular displacement points away from each other by the distance L. You can then allow for a radial displacement equal to L times the tangent of alpha, and alpha is the allowable angle of displacement. And typically a coupling will be rated for around 1 degree of displacement. So if you have 1 degree displacement and a double flex coupling, you can get a certain amount of radial deflection. The far longer that coupling is, the farther distance between the two flex points, the more radial. And there are actually certain couplings that have big tubes in the middle between the flex points to allow for extended amounts of radial misalignment. So these are some pictures of couplings. On the left is a single flex coupling. We always recommend steel disc type couplings. The reason for that is they are very torsionally stiff, but they're also very flexible in the angular direction, and they ensure the flex only happens at a well-defined point right in the center of the disc pack. And on the right, we have a double flex disc coupling, similar design as the one to the left, but it has two disc packs separated by a plate. Again, very well-defined flex points right in the center of each disc pack. They're separated by distance, so the coupling on the right can allow for some radial misalignment, whereas the coupling on the left does not displace at all radially, very, very, very minimally, but it does deflect quite nicely as an angular direction. And then these kind of couplings also deflect axially, which is important because, again, if you put two shafts together, you start spinning the motor, everything heats up, the shafts grow, the distance between the shafts actually decreases or increases depending on the situation, and that'll create, say, tension or compression in the driveline. The coupling flexing allows that to happen without damaging bearings or creating any kind of errors. In the middle bottom there, we have a spiral cut coupling, which is a very miniature type coupling. That's not a great coupling, but again, when you get really small, it becomes challenging to make disc type couplings. Moving on. Again, some pictures of couplings. The coupling on the left is a keyed coupling. Again, it's okay. Certainly on the customer side, it's fine if they want to use a keyed coupling. On the transducer side, we recommend against it, but customers require it, and we provide keyed shafts on the sensors as required. Again, just not preferred. And that one is an example where there's a spacer tube between the two disc packs. So the coupling on the left as a double flex coupling allows more radial misalignment than the double flex coupling shown in the previous slide. On the right, actually, I should say, sorry, in the middle is a single flex coupling. It shows the example, though, of a gripping type hub for smooth shafts. The screws on the end of the hub, as they are tightened, they pull that collar down on a chamfered bore that has a split in it. And so as that ring is pulled down, it actually grips the coupling onto the shaft. And then if you were to release those screws, it opens up and the coupling can be slid off the shaft. Actually has a feature where you can take those screws all the way out and then insert them into the free holes that you see, and they can use to actually jack the ring off of the hub, because it may not want to come off depending how long it's been on there and how tight it is. So a feature for removal. One thing that should be noted, when a coupling bore is specified, it's quoted with an allowable bore range. So a particular coupling might say it can have between 14 and 25 millimeter diameter shafts. What that means is it can be bored to any diameter to accommodate a shaft between 14 and 25 millimeters. So if you have a 22 millimeter shaft, the bore can be cut to 22 millimeters. It does not mean that the coupling shrinks down enough to take, a 14 millimeter shaft in the 25 millimeter bore. So the bore quoted is allowable. As ordered, the coupling will be cut to the exact bore size for that specific shaft, and typically very tight tolerance. So the shaft might have a G6 tolerance, and the hub might have an H7 tolerance, which is a tight but not a interference fit. So be a line fit where it slides together without a lot of slop, and then it can grip down as you tighten the hub. The reason for that is this is steel, so imagine it doesn't deflect all that much. So you need very tight clearance before you start gripping. Otherwise, it doesn't deflect enough to get a good grip. On the right, a bellows coupling. These are acceptable type couplings. It has a clamping hub where you see you tighten the screw and it closes a C-shaped collar that grips onto the shaft. And then the same thing on the right, except that one has a flange mount on one end and a shaft on the other. This is not recommended. We actually had a customer do this. Thought it was pretty funny. Next slide. So this is what happens when, say, improper coupling is installed. This is actually a customer made their own coupling, and they use a set screw by, drilling a hole through the coupling hub and tightening the set screw against the sensor shaft. Well, what happened? It slipped. Guess what happens? As soon as it slips a little bit, it keeps slipping. And so here the set screw spun round and round on the shaft end. And this basically ruins the sensor. You can no longer slide a coupling hub on or off without further damage. And basically it's ruined, or you could potentially machine the shaft to a smaller diameter to clean it up. But it's hard to machine a shaft that's actually installed in a torque sensor. Cutting fluid, cutting loads, those kind of things can be quite damaging to the sensor. So usually these are scrapped at this point. Or you can rebuild it by replacing the shaft and maybe saving the electronics, some of the electronics, but undesirable. Moving on. What happens as that shaft spins, or the hub spins on the shaft? This one got very, very hot. And you can see the aluminum housing actually got hot enough that it sagged down. So you can see where the connector used to be. That's actually bent down due to basically the cable weight and the extreme hot. Apparently this was glowing red hot. And it's very interesting because the customer called up and said he thought the torque sensor was defective. And so he sent it in, and I looked at it and said, wait a second, something going on here. And when I called him back, he said, well, yes, it was glowing red hot. I said, okay, probably not defective. I think you had a mechanical problem. Next slide. Floating mount versus fixed mount. Floating mount, the sensor is supported only by the drive and load side connections. and they would use single flex type couplings for that. A flexible strap keeps the sensor housing from rotating. And when I say flexible strap, be a spring or a rubber strap, not a rigid mount. And then bearingless sensors are always floating mount because the bearings cannot support the weight of the shaft or the sensor because there are no bearings. So the assembly sensing element must be supported by its end connections, which means it floats in the middle. And that would be, say, between a motor and another motor and a transmission, motor and a brake. Fixed mount only applies to sensors with bearings because it talks about housing, holding the shaft, and then that housing mounting to, say, a plate. When used such a way, it's just really for alignment and support of the shaft. It's not at all intended to be used as a bearing block or a jack shaft or anything. Because again, the bearings in a torque sensor are not a consumable item that is readily replaced. So you don't want to use the torque sensor as a bearing block and wear out the bearings. We'll show some examples in the next coming slides. So here is an example of a floating mount sensor installation where you have the blue sensor in the middle. You have single flex coupling on each end of the shaft, and then you have a motor spinning through a plate, spinning the assembly, and you have a gearbox on the other side reacting the torque or creating the load. And the torque sensor hangs in the middle. And the only thing that keeps that housing from spinning along due to the bearing friction is a flexible strap, which again, in this case, is literally a tension spring held between a threaded hole in the sensor housing and the plate. So it allows it to articulate. And when we say articulate, it's impossible for the driveline shaft and the load shaft to be perfectly concentric at all times. Even if you say use special lasers and adjust them, each of the items will have run out. So as these items rotate, their center lines don't, or the shaft doesn't rotate exactly around its center line because of the bearings and everything in the system. And so both shafts are going to be spinning with their centers, say, moving relative to each other. And so the couplings allow the torque sensor to sit in the middle, and then the whole system articulates a little bit. So that torque sensor actually moves around a little bit due to the run out in the drive and the load device. And the flexible strap just keeps it from spinning, but it allows it to articulate. Next slide. So the pros of a floating mount is it's relatively more misalignment can be tolerated. Because we talked about earlier, the farther you spread the disc packs apart, the more radial misalignment is allowable. And the single flex on each end of a shaft is quite a bit longer than, say, a double flex coupling, where the shaft, say, on each end has a double flex coupling, but then the coupling discs are only separated by a plate, which might only be, 12 or 20 millimeters, something like that. So quite short. Sensor is protected from radial and thrust load damage. If there's a single flex coupling on each side of the shaft and it's truly floating, you cannot apply any bearing loads or any bending or any side loads to the sensor because the couplings move instead of the load being transferred. These are lower cost. Single flex are lower cost than double flex couplings. Also quite a little bit shorter drive line. Again, say real estate, test bench, space, cost, so a smaller footprint can be lower cost overall. Cons, the sensor's unsupported. So say you have a system where you're going to test motor after motor after motor. Every time you disconnect the test article motor, the whole sensor can flop over. So it's not supported. That can damage actually the coupling that's on the other end of it. So if you're going to break the drive line a lot, a supported foot mount sensor might make more sense. Again, more unsupported mass for high RPM use. It may be better to have a pedestal mount where you have two shorter spinning sections with coupling versus the entire assembly of the torque sensor housing as mass supported in the rotating section. And then Cons of this is it's important that the sensor truly floats, and some customers will kind of mount the housing of the floating sensor, say in some kind of a cradle or something, and that might seem okay, but typically it constrains or constricts the movement of the sensor too much and is not desirable. Again, as soon as you say mount the housing of the floating torque sensor rigidly, it really becomes a fixed mount. And a fixed mount sensor with only single flex coupling on each end creates damage to the bearings and side loads and bending and radial loads. Next slide. So here's an example of a fixed mount where we have a drive and a load with a torque sensor that's a pedestal style mount mounted in the middle. Then you have a double flex coupling on each shaft end. Moving on. So pros of a fixed mount installation would be that sensor is supported while connecting and disconnecting the test article. Can be better for higher speed because you have shorter unsupported rotating sections. Cons, it requires more expensive double flex couplings, has relatively less misalignment capability because the couplings are short with just a little plate in between the flex points. Sensor can be damaged by unsupported masses, radial and thrust loads, not as well protected. The bearings or jack shafts shouldn't be used to prevent this. So a lot of times you might have an extra bearing that goes into the test setup, and that test setup maybe takes overhung moment. So if you're going to have a torque sensor that has bearings, you don't want to use those bearings to support any radial load, but maybe there's some radial load that needs to be supported. For example, if you have a fan and you're trying to test a fan blade, you could potentially mount your fan straight to the torque sensor shaft and then see how much torque it takes to spin that fan. Well, that weight of the fan is going to create a overhung moment or bending on the shaft, and that may be damaging. And so what we would recommend would be a coupling between the fan and the torque sensor and some kind of intermediate bearing to support the weight of the fan. Again, do not use the torque sensor as a bearing block. Bad idea. We don't want you to ruin torque sensors. Moving on. Again, this is another possible installation. The two more recommended and more common installations would be a straight floating mount with single flexes on each end, or a fixed mount with a double flex coupling on each end. Here we show a rigid coupling on one end, and then you can imagine, depending how much run out there's in the drive, the whole other end of the torque sensor shaft is going to rotate in some arc as it spins around its center line. You have a double flex coupling at the other side to accommodate that. And this wouldn't be good for, say, high RPM use, or, this would be a limited use case where sometimes this makes a lot of sense, but it's typically not the most recommended. And then if you replace that double flex coupling with another rigid coupling, now you'd have problems. The sensor will be damaged. Next slide. So you may have heard me say bearings versus bearingless. Some rotary torque sensors don't have bearings, so they have some kind of a stator which has electronics in it and provides power to the rotating assembly, but there are no bearings to hold those two pieces, the rotating and the stationary piece, near each other. And typically they need to be very close together. So if you have a rotating part and a stationary part, they can't be 20 centimeters away from each other. They have to be held with a pretty close gap. Typically, it may be on the order of 1 millimeter. And so the bearingless sensor has to have some method of holding that sensor and the stator closely together. Advantages of a bearingless sensor is there is no bearing friction, and we spelled bearing wrong here, seems, but anyway, bearing friction is something that, say you're trying to test a bearing and measure how much friction that bearing has under certain conditions, the bearing friction in the sensor might actually contribute, and you may not want that as part of your measurement. And so a bearingless sensor eliminates that. Also, one of the things with bearing style sensors that happens is the bearings wear out. Now, if the proper couplings are used and they're used within their RPM ratings, they should last a very long time. But in many cases, there may be some kind of extraneous loading and thing. Maybe the couplings aren't perfect. There are other types of couplings that we didn't talk about that are less desirable, rubber type couplings and things that do create some bearing loads. So the bearings can wear out. Bearingless, clearly you're not going to wear the bearings out. There are no bearings. They always are floating mount because, again, the sensor is only supported by its end connections. There's no housing with bearings supporting it. And that's it. So accuracy and resolution. Usually quoted as a percentage of the capacity. So it's a 100 Newton meter sensor. There's a combined error of 0.1%. That would mean 0.1% of 100 Newton meters. And that would be a 0.1 plus or minus 0.1 Newton meter error. Now, that's great, except a lot of times you may want to use a 100 Newton meter sensor to measure 5 Newton meters. And you might need to do that because of other extenuating circumstances in the application. So that is one thing to consider. As the sensor becomes larger, the errors tend to increase as a Newton meters. The percentage stays the same, but the actual error becomes larger as the sensor gets larger. You have temperature errors. You also have noise and resolution that contribute to your ability to measure accurately. And then measurement bandwidth and sample rate are to be considered. Trying to take very high dynamic measurements, you need to run high bandwidth. Trying to get very high resolution, you may want to run heavy filtering. Those two don't necessarily go together. So again, there are compromises that need to be understood when deciding what appropriate, say, uncertainty or error budget is for a system. So there's always a compromise between accuracy, resolution, and safety factor. Moving on. Here are some examples of specification pages for various different torque sensors. So you can see if you're going to be comparing, they have something called a combined error. You have 0.1, 0.2, or 0.25%. In the case of these torque sensors, there's their non-repeatability spec, which gets a little worse as you go from model to the right. And then we also have a resolution. And so say the higher accuracy sensors typically are 16-bit or more. Many of them are 24-bit. Most times the 24 bits are not usable. So you might have 17 or 18-bit max out of a 24-bit system. 12-bit is less resolution, obviously. And then to the far right, sometimes it's not a bit. If there's not an analog to digital or digital analog converter, there is not a bit resolution. So the sensor on the right uses a frequency converter, and that's typically considered an analog device. And so the resolution is considered analog. The limit of your resolution, though, is going to be noise. So you can have, you have 24 bits, have millions and millions of counts of resolution, but if a lot of that resolution is noise, it is not usable. So keep that in mind too. The limiting factor a lot of time is noise, not actual electrical resolution of the sensor. And noise can be mechanical, can be induced by motor drives and things, induced into the measurement system, can be induced into the torque sensor. Analog output can also be induced into the device that's being used to measure the analog output. Can be grounding, noise due to variable frequency drives and things. So a lot of times there can be a significant amount of signal noise in a torque system that limits the resolution. Moving on. So very typical signal types, 5 volt, 10 volt. Some sensors will have a frequency output. You also have digital outputs such as USB or RS-45. Almost exclusively, and I can't think of an example that would not be bipolar. All torque sensors are bipolar, and that if it says it's got a 5 volt output, what that really means is it measures plus or minus 5 volts. It measures 0 volts at 0 torque, and then say under a clockwise torque, it goes from 0 to plus 5 volts, and then counterclockwise torque, it goes from 0 to negative 5 volts. So there's really not a case I can think of where it would only say work in the clockwise direction. Now, sometimes customers cannot measure it cannot deal with a negative voltage, so we can offset the voltage. So we could have a 5 volts at 0 torque and then say 0 volts at full counterclockwise and 10 volts at full clockwise. So that's possible, but that's a special, and typically they're not set up that way unless specified. Frequency would be, instead of a voltage, you might have a frequency output, might be 10 kilohertz at 0 torque, and then it might go up to 15 kilohertz full clockwise. It might go all the way down to 5 kilohertz full counterclockwise. Of course, USB to RS-45 would be delivering processed data, so Newton meters as a digital packet. Can digital versus analog? The analog sensor can't have something like RS-45 or USB. Digital sensor may be digital internally, but then converts back to analog for the signal. We talked about bit resolution and noise already. So capacity selection. Torque sensor is a little trickier sometimes in load cells. People kind of have an idea what 100 pounds is. So you're trying to estimate, oh, you know, your thing weighs 100 pounds. You want to press another 50 pounds. You need a 150 pound, maybe a 200 pound sensor. You know, fairly easy in a lot of cases to estimate or to know what force you need. Now under impact loading, not quite so easy. So if somebody said, okay, I'm going to hit this load cell with a hammer, what capacity do I need? And surprisingly, you might need a lot higher capacity than you might expect. Well, same thing with torque. Torque is rotating in a lot of cases. And so you have dynamic conditions to consider. And so it's not just a simple, this much torque. Now, if you're testing a valve, it might just take a certain amount of torque to turn the valve. That may be easy. But if you say a motor spinning a compressor, and you're trying to measure how much power that system requires, there's a lot more going on than just applying a constant torque. There's compressor pulses, there's motor pulses as the poles of the motor are spun past. And so basically you have to figure out what the capacity needs to be. And torque sensors always have a capacity. They also have a safe overload range, and you want to reserve that safe overload for accidents. You never want to factor in using the safe overload as part of your measurement range. It's always designed for extra overhead safety factor in case of accidental loading above design intent. You can calculate the running torque average sometimes. So if you have a motor, you can say, okay, that motor is rated for, so many kilowatts at X number of RPM. That'd be the motor rating. That means if you turn the motor on, let it spin, and then load it, X number of kilowatts, they'll be running at certain RPM, and that's on the nameplate of the motor. So you can actually, and they don't say how much torque the motor produces typically on the nameplate, but you can calculate that. And so if you know the RPM, the speed of the system, and you know how many kilowatts the motor is, you can actually calculate that. And so it's kilowatts times 9550 divided by RPM equals Newton meters. So what that gives you is the average running torque. Doesn't mean there aren't a bunch of pulses and spikes. That's just what the average running torque is. You need a torque sensor that's larger than the average running torque. And, how much larger? Well, we're going to talk about that. So when you decide how much larger it needs to be, you need to talk and think about what the load and drive service factors are. Some loads and drives are much harder than others. You have startup and inertial loads that can create a lot more torque than the average running torque, and then extraneous loading also. So drive service factors, from light to severe. As in spinning a smooth turbine, it spins smoothly. There aren't any pulsations. Our DC motor, three-phase AC motor, they spin and create torque in a smooth manner. A little more severe, but not bad, would be something like an 8-cylinder gas engine or a 10-cylinder diesel, a single-phase AC motor. They spin quite smoothly. And the 6-cylinder gas or 8-cylinder diesel or 3-phase VFD motor, a little harder. And then 4-cylinder, you kind of get the trend here, 6-cylinder diesel, a single-phase VFD. And then on the worst case, you have something like a small engine with 4 cylinders or less, or a 6-cylinder diesel. Imagine a 1-cylinder diesel engine go thump, thump, thump. So your average torque might be relatively low, but every time that piston fires, you've got a gigantic torque spike come down the line. And those kind of motors might have, say, a large flywheel to dampen that out in their application. But during testing, likely the flywheel might not be involved, and you have the torque sensor directly coupled to the shaft. Say if you're trying to measure, the features of that piston firing. And so the average torque is going to be maybe pretty low, but the impulse will be very high. So you have to kind of consider what the drive service factor is. And moving on, you also have a load service factor, which is the same idea, except what is being driven by the system. That has a characteristic also. And again, a smooth thing like a fan or a blower, that's quite easy to spin. Something that's non-reversing like a conveyor or a mixer, it basically just keeps turning, maybe a little more difficult, but not terrible. Then you might have shock or reversing loads, crushers, hammer mills. Hammer mill sounds like a severe load. Single cylinder or reciprocating pumps, things that basically as you're spinning them, they get harder and easier and harder and easier to spin. And those create torque spikes in the driveline. And then worst case would be like heavy to full torque reversals, undamped torsional vibrations. So certain RPMs, certain stiffnesses in the driveline, you can get vibrations. If those are undamped, they can be very severe, which create large torsionals, things like that. So you imagine if you have a very hard drive service, so say like a single cylinder diesel, and you had a very difficult load like a hammer mill or something, or a grinder, you would have to say multiply by a factor of maybe 5. So it's 100 Newton meters average running torque. You might need a 500 Newton meter sensor. And then you have to consider starting conditions. And if you start up a electric motor and just apply power to it, it'll start to spin and try to spin, and its torque it can produce during start conditions can be much, much greater than the actual average running torque. And that may be something too that a motor test might want to measure that. So you basically lock a brake, turn on the motor, and see what the torque is. So that can be a lot higher, as in 5 times higher, 2 times, 3 times higher than the actual rating of the motor. And then same thing when you stop. A lot of systems, because it's rotating, it's somewhat dangerous. If somebody's shirt or something gets caught, you need to stop it immediately. And so there might be a red stop button and somebody hits it. Well, that stops, maybe applies a brake, maybe kills the power of the motor. What that does is, if you say you're spinning at 10,000 RPM, you have a lot of stored energy. If you try to stop it, that rotating inertia may overload the sensor as it starts to slow down very quickly. So kind of the similar thing as a startup torque. If you stop quickly, the tendency of the driveline to keep rotating may destroy the sensor. And we've had customers who have ruined torque sensors and say, well, what happened? No, nothing happened. It was running great, but somebody hit the emergency stop. And that may be good. If you have to hit the emergency stop to save somebody from getting hurt, great. But it shouldn't be used as a standard stop method because they can be damaging. Note, peak torque can be 10 or more times the average running torque. So you have to figure out what the peak torque is going to be and size your sensor appropriately. And sometimes it's not possible to know exactly what the peak torque is. That's why you're using a torque sensor in some cases. So it needs to be sized. Maybe in the end, you oversize the torque sensor. You take high frequency, high data rate torque data, and then find that, okay, the spikes aren't as high as you thought. And now you can maybe downsize to a smaller sensor if you want more accuracy. On the other hand, if you size it too small and run it, you'll find you ruin your sensor, and then you'll have to upsize. So it's usually better to start higher and move to a smaller sensor later than to start too small and damage it. Because if you move down, your bigger sensor is something you can use later for something else. But if you ruin the smaller sensor, it's not useful anymore. So moving on. Extraneous loads. These cause errors. So we talk about using couplings. Sometimes extraneous loads are not able to be eliminated. For example, with a reaction torque sensor with a large mass, say, hanging on the torque sensor, it might be that that extraneous load as a bending moment or overhung moment cannot be avoided. So what has to be done is you have to size the sensor up. They typically have a rating for allowable overhung moment, and you need to find a sensor that can withstand the amount of overhead you will apply. And it could be that that makes the sensor much, much higher capacity than you may want, but that's just how it works. You can't have a very small capacity sensor withstand a very high overhung moment, for example. So you may have to size up the sensor due to extraneous loading also. Moving on. So this is an example, dual range sensors. We have our model T6 and T7. ATQ can be had in a dual range configuration. This shows our older HRDT. We sold a lot of those with dual or even triple range configurations. But just keep in mind, it's not a magic bullet. There's no magic to a dual range. It's not like you have a, mechanically overload protected low range. Typically, it's the same range sensor, but with extra magnification or amplification on the low range signal. And if you're going to do that, it sometimes makes a lot of sense to do it right at the measuring section. So in like a dual range torque sensor, there's strain gauge amplifier right at the bridge, right on the rotating shaft, and the amplification is done there. So you're amplifying as close to the bridge as possible, so you're not amplifying noise that gets in post, anywhere downstream. So dual range can be quite nice for a few reasons. It may be more convenient, less fixture changes. They had two different size motors to test. You can test them in the same setup. A lot more safety factor. Again, if you're not really sure, or you have large spikes, but you also want to measure, say, bearing drag or something in the same test, you might want to have two ranges. They are compromised though. It can be noisier. The low range does have more gain on the signal, so any noise in the system does get amplified. Typically, you want to run heavier filtering. That may not be desirable depending if you're trying to measure something with high bandwidth. Temperature sensitivity, the lower range is more sensitive to temperature. And then again, you have large fixtures. So say you have a 10 Newton meter and a 100 Newton meter dual range sensor. All of the coupling and everything are basically sized for 100 Newton meters because they have to be physically large. And again, the shaft size on a 100/10 Newton meter sensor is going to be sized as 100 Newton meter. Moving on. All right, all sensors will have a maximum RPM rating. If they're bearing style sensors, sometimes the bearings are the limitation. Also, some rotating electronics due to G-forces and things. As the capacities go up on the sensor, typically their diameter goes up, and that means the bearings diameter goes up, and also the radius of the rotating electronics gets greater. So in almost all cases, you'll find that there are RPM ratings of sensors, and those RPM maximum ratings decrease as the capacity goes up. So a sensor might be rated for 30,000 RPMs at 1 Newton meter, and then the 1,000 Newton meter version might only be rated for 5,000 or 10,000 RPM. That's pretty much a law of physics. It doesn't change. Somebody says, "Oh, I want to buy that sensor that's rated for 30,000 RPM at 1 Newton meter, but I need it at 1,000 Newton meters, and I still want it at 30,000 RPM. Well, if that were easy, we'd already have done it. It would be the specification. So the fact that it says it can only run at 5,000 RPMs, that's a pretty hard limit. Not like, oh, we'll just have to, do something else. Because if that something else was easy enough to do, we'd have already done it. So the ratings are typically maxed out as they are on the data sheets, and they don't have any, extra wiggle room. Some of the things too have to do with bearing life. And if you talk to a bearing manufacturer, how long is my bearing going to last? They won't tell you. There's all kinds of variables. So RPM is one of them. Load, heat, lubrication, all of those things come into play. And so the ratings listed on the data sheets are intended to allow the sensor to operate under those RPM conditions for a good long lifetime without wearing out the bearings. Balancing. The higher something spins, the more important it is for the system to be balanced. The sensors are typically inherently pretty well balanced. Couplings are reasonably well balanced, again, because they're symmetrical. But It's not just the sensor, just the couplings. The entire rotating assembly needs to be in balance. And a lot of times that would include balancing the entire rotating assembly as an assembly, not individual pieces. So it should be considered. A lot of times if you're talking to a customer, you might ask them, what their balancing plan is. If they're talking about higher RPM, 10,000 RPMs, what's your plan for balancing? They may or may not have any idea. If they don't, we're not experts on it. We can't balance their assembly, even if we provide a balanced sensor. The rest of the components in their driveline also need to be balanced. So something the customer really is responsible for. Say the limit on balancing and RPM might be bearings, G-forces on rotating parts, etc. So some common, say, special features would be hollow. We talked about that, where you might want something to pass through the rotating sensor. Some sensors, you can change the scaling. Like our ATQ, you can go in and adjust, 10 volts equals 100 newton meters, or 10 volts equals 500 newton meters on a 500 newton meter sensor. Might have selectable outputs. Again, some of them you might have a voltage, milliamps, or a frequency available depending on what you select. Filter levels, sometimes they have fixed analog filters. Sometimes there are adjustable digital filters. You might have some special options or versions of Tork sensors to go to higher RPM. Speed or angle measurement is interesting. For measuring power, you need not only a torque, but a speed measurement. It's nice if that's integrated into the torque sensor. Also angle, doing a valve test or some kind of a test where you're measuring torque versus a specific angle. The angle encoder integrated into the torque sensor can be handy. And then we also have some options for high pulse per revolution encoders. Specifically our ATQ, we're soon to introduce some much higher pulse rate encoders that are integrated with the body of the sensor as a kind of an add-on, but nicely integrated. And there might be, say, 4,000 pulses per revolution or 40,000 pulses per revolution. Somebody's trying to measure something with very fine angle resolution. You need a lot of pulses. Also, very fine control of speed. You need more pulses. Moving on. Here's an example of a brake test. This is our model 5412, 50,000 inch-pound torque sensors, which is about called about 5,000 Newton meters. You can see that rotor is being tested, is running red hot. The spinning assembly is attached to the brake disc that spins, and then the caliper is actually attached to the part that's attached to the torque sensor. So it's a reaction torque sensor measuring a rotating, or being used to measure torque generated from a rotating brake. Commonly done. Moving on. Here's a example of a fuel pump optimization, or a customer wanting to, say, tune a fuel pump to optimize fuel flow versus power. Say for a race engine, important to minimize the power, maximize fuel flow. This would be a pedestal mount, happen to be model T5 sensor, double flex couplings on each side, torque sensor, a basic digital display for the readout, and the motor mounted on a plate, and the fuel pump mounted on a plate measuring the torque. Moving on. Here's an example I mentioned earlier, this model T22. Basically, you have a pulley on the end of a motor shaft. You can take that pulley off. You can make a special pulley that mounts onto the T22, and then you mount the entire T22 onto the motor shaft. So the T22 has a bore, which you can see on the left side. It is keyed. And we say we don't like keyed hubs. Well, this type has to be keyed because you really can't make this shaft grip onto, or this hub grip onto a shaft, because there's no method for doing that. So it's a keyed hub that slides onto a shaft, and then the pulley mounts to the bolt circle that you see on that torque sensor. And then the blue part is really just an assembly that allows the rotating electronics for the signal and power transfer. So the entire shiny part spins along with the motor shafts, and there's a pulley attached to that. You can see in the picture on the right, there's a belt, and that belt tension is reacted by the motor shaft, not the torque sensor bearings. And so the torque sensor housing is just kind of there along for the ride. Think of it as a slip ring assembly. It's induction, but it's the same idea as you've got a little slip ring thing there at the end. And then you got, torque and speed, conventional power. This shows our model 9850 digital display for that. Moving on. Here's a drive line test. A steering column test. This is an actual customer application. They sent me that little sketch. So I threw it into the presentation. It's very helpful when you ask a customer, please send me a sketch. A lot of times they'll be talking about something they're super familiar with, and they may make steering columns. And the only steering column you've ever seen is with a steering wheel attached to it in your car, right? So you don't really know what the rest of it looks like. Have them send you a sketch. How are they going to mount it? And now you can talk to them with a sketch, or have them share the sketch as you're doing a Teams meeting or whatever. So in this case, they sent a sketch. We decided, because it wasn't actually going to spin very much, we could use an MRT, which is a reaction type torque sensor. And they actually added their own encoder into the system. And the steering column is actually shown there on the lower left. But that's what the test assembly looks like. And they added a brake so they can apply a load as they twist the steering column back and forth, simulating somebody driving down the road for hours and hours. Moving on. This is an installed flange type torque sensor, something like our model ATQ, with couplings attached on each end of it between two electric motors. In this application, we had a college, MIT actually, Massachusetts Institute of Technology, who was fielding an electric vehicle in the SEA Formula Car competition. And that competition, basically colleges create vehicles that they race, and the college students, manufacture the car basically, and then race them. And it doesn't really look like that car on the left. That's an actual car you could buy, whereas the cars they make, look more like go-karts. But in any case, the engine, it was replaced, the internal combustion engine that were typically used was replaced with electric motors. And they wanted to test those motors because the specifications from the manufacturer aren't necessarily the ones they need to know when they're designing the car for, best performance on the track. So they needed to actually characterize the motors themselves. And so they're going to use two motors in the car. So conveniently, they were able to use one of the motors as a drive and one as a brake, and kind of fight the two motors against each other, spinning one, loading with the other. And they could characterize the motors with a torque sensor in the middle. And the torque sensor is measuring speed and torque. Moving on. I guess that's it. We're now ready for any questions, and I'd like to thank you for sitting through the presentation too.
Yes, Keith, thank you very much for your presentation. We have gone a little over our time, but it was really comprehensive and descriptive. And we have some questions for you. Emre Bey has a question. He asked, after the installation, how could we monitor the torque value as real time? Is there any PC software in interface solutions? How do they communicate each other? Can torque and speed values be monitored in different indicators or data acquisition systems without interface products? If you inform us quickly about instrumentation selection, maybe it will be beneficial to for this question.
All right, good question. As you point out, there always needs to be something reading or measuring the signal from the torque sensor, and that thing, that item, the instrument is and also can contribute error and is part of the measurement system, so it needs to be considered. For most basic testing, sometimes a standalone display is useful. That might just display torque, or it might display torque and speed, or calculate horsepower. Might have limited bandwidth, might have low sample rate. That may be okay if somebody's just trying to measure, say, average running torque, not interested in dynamics. There are also torque sensors that have software included, that have digital outputs. Those software packages typically display graph and log data, and they have adjustments that can be made for filtering and bandwidth and whatnot. We also have instrumentation that runs relatively high bandwidth. So if somebody wants to measure, say, high dynamic, features of a torque signal, we do have boxes that basically would sit between the torque sensor and a PC that can take the signal, maybe sampling up to 40,000 samples per second, and that can be turned down or decimated, but you have a high sample rate internally, and so you can say capture spikes or features. We can also obviously hook up or attach to data acquisition systems that are already deployed at a customer. Sometimes they might be using something like LabVIEW, and they might want an instrument that has LabVIEW drivers or VIs. We do have certain instruments that do have those. Or again, if the data acquisition system has a voltage or a milliamp or a frequency input, we can accommodate that by selecting a torque sensor that has the appropriate signal to connect straight to the data acquisition system. So very important consideration, though. We've had a number of customers who over the years maybe start complaining, that their torque sensor broke, and they show you the graphs and say, it's only 40 Newton meters and it's a 100 Newton meter torque sensor. How did that happen? Then you start digging in and say, the sample rate was only 20 samples per second, or they had very heavy filtering. And you say, what did the raw data look like? And sometimes they'll have the raw data. And then you say, it has these gigantic spikes. And so maybe the spikes are 150 Newton meters on a 100 Newton meter sensor. So it's important to consider data rate too, even if you don't really care about, high bandwidth measurements. If you take, say, a slow measurement rate or apply heavy filtering and something happens, say there's torque pulses that you don't expect, you can't see them. And if they're filtered out, you cannot, they're gone. So if you take high sample rate data and filter it afterwards, you can then have the, ability to look at it and see what was really happening if, say, an event takes place, say an emergency stop. You want to see what was that torque spike. Well, if you're sampling it too low or applying too heavy a filter, you missed it and you'll never be able to get it back.
Yeah, thank you. Emre Bey, bu konuda da bilgilendireyim. Interface'in web sitesinde bu enstrümantasyon seçimleriyle alakalı belli başlı hazırlamış oldukları uygulama notları var. Bizimle iletişime geçerseniz beraber de o ürünleri inceleyebiliriz. Yes, Keith. Also, Melis Hanım has a question about some strain gauge application. Can you see that question in chat part? Melis Tork Hanım.
Strain gauge application. Yeah. Well, I think that question to say you have a strain gauge device and the math says the output should be X, but it's actually X times 2 or something higher than expected. So instead of 10 millivolts, one thing I say is that's why we sell torque sensors. So sometimes the math doesn't match reality. So it may be that the steel or whatever the component is, the strain gauge may have similar, say, elastic properties than expected, may not be to spec, may have a different hardness or something than intended. Also, the strain, if you did an FEA analysis on that exact structure, you might find that there's some strain concentration that you're not expecting where the strain gauges are. but typically the strain gauges don't lie, so probably there is more strain than expected. That would be my thought. And we had a number of guys, for example, we had an electric vehicle motor manufacturer who had X amount of power expected from their motors, and they were calling, complaining because torque sensors were wrong because they're only getting about half as much power as they expected. Well, in the end, they were only getting about half as much power. So sometimes the test tells you the truth, and the theory didn't work out as expected.
Thank you. And Zafer Bey has a question about three-phase PMSM motor generator test bench. Can you see that?
That's a very good question. Three-phase motor, better than a one-phase motor. If the nominal torque is 300 Newton meters, you could easily exceed 500 Newton meter under certain conditions, say startup or stop if there's a lot of inertia, depending what's being driven. You have a motor, but what is being used as the load. So I would say you certainly wouldn't want to use a 300 Newton meter sensor. 500 may be okay. 1,000 Newton meter might make more sense, but you do have to consider not only the motor, but what is being tested. Is a gearbox? What happens if failure? We have certain customers the test, say they 100% test a system, and every one that comes off the assembly line gets tested, and they run fine. Then they ruin the torque sensor. It's, the torque sensor went bad. You say, well, what happens when the device fails the test? Oh, the bearings lock up. Okay. So, you're spinning at some RPM and the test device fails, you can get quite a higher torque than the running torque. So, it's hard to say specifically, but I think you're on the right track to upsize at least to 500 Newton meters, maybe 1,000 would make more sense depending on the other considerations.
All right, thank you. Lastly, Ahmet Bey requested from you to open slide 43. Can you open it? And Ahmet Bey, if you have any question about this slide, you can write now to the chat part.
So this is slide 43?
Yes,
yes.
This is right. Yeah. Okay then. Is there any question? It seems there is no any question anymore. So,
well, I'd like to apologize. I went over time. Usually I talk faster, but I was sleepy, and it's early in the morning here. So.
Zafer Bey sent their comment. 1,000 nanometer sensor because the accuracy is less. Do you have any opinion? Keith, did you see Zafer Bey's comment on chat part?
Oh, sorry. Well, you don't want to choose 1,000 Newton meters. There's always a compromise. So again, be careful. The 500 can be okay. You want to measure with good bandwidth and monitor and make sure you're not exceeding 500 Newton meters.
Okay, thank you. Thank you for everyone to participation. Looking forward to meet with you in our next webinar. So thank you very much.
All right. Well, thank you everyone for your time. I enjoy doing these. So does Jeff. And we'll talk to you again someday.
Hopefully. Bye-bye.
Bye.